All right, in this section, we're going to continue talking about how we can compare two populations using statistical inference methods. And in the last section, we talked about how we can compare two proportions, the proportions from two different populations using a confidence interval or using a significance test. In this section, we're going to do the same thing, talk about confidence intervals and significance tests, but now we'll be talking specifically about comparing two means. All right, so it's going to be really similar to the last section, really repetitive, all the same ideas, but just talking about means instead of proportions. So to briefly summarize, the key differences we know for means versus proportions is that we'll use t as our test statistic in critical value rather than z. That's really the main difference. And then within that, when we do our conditions, we'll want to check for the normal condition, we don't check the large counts. For means, we'll check large sample, and or we can just look at the actual distributions themselves for skewness or outliers. So again, key difference between proportion and means. For proportions, we use z. For means, we use t. And for proportions, the condition we need to check is large counts. For means, we check large samples. So let's talk briefly through what the shape of the sampling distribution would look like for the difference of two means. It's really similar to what we saw in the previous section for proportions, right? If this is the sampling distribution for the first population's sample mean, and this is the sampling distribution for the second population's sample mean, the sampling distribution for the difference between the two samples means would be just the difference of the sample means. So that would be the center, 0.67, right? So we can find the average difference between two populations by taking the average difference, or the difference of the averages, right? We've seen this rule repeatedly here for the average of a difference of two random variables is equal to the difference of the average. But we know that that's not true for standard deviation. For standard deviation, we have to add the variances together. Again, that same typo there. We have to add the variances together. We cannot add standard deviation together. We cannot subtract variance. We have to add variances together. When we do that, so we're saying if we want to find variance of the difference of two sample means, that's equal to the sum of the two sample means variances, right? And we know that variance is just standard deviation squared. But if you remember, standard deviation for a sample mean was equal to standard deviation divided by square root of n. And that's what we're seeing happening in here, right? So when we want to talk about the variance of the first sample mean plus the variance of the second sample mean, we'll take the standard deviation of the first sample mean, square it, and then add the standard deviation of the second sample mean and square it. And then we'll just do a little bit of algebra here. When we square the top, becomes sigma squared. When we square the bottom, gets rid of the square root, and we just get n. So then this is our variance for the difference of sample means. And to get back to the standard deviation, we would simply take the square root. And so here's our formula for the standard deviation of the difference of sample means. Standard deviation of difference of sample means given by this formula. This is given on your reference sheet, okay? So we don't need to memorize that. We need to know how to substitute it and when to apply it. That's the key. All right, so shape, outlier, center, spread, that's how we describe a distribution. So when we talk about the sampling distribution of a difference of sample means, we see that the shape of the sampling distribution, if the parent populations are normal, the sampling distribution will also be normal for the difference of sample means. In other cases, it will be approximately normal if sample sizes are large enough, right? So the shape of the sampling distribution for difference of sample means is approximately normal if the parent populations are normal, or if we know that both samples are sufficiently large. So large samples condition, but applies to both samples. The center, the mean, will be given by just the difference of the population means. Okay, the average difference of sample means is exactly equal to the actual difference of population means. And the spread is described by the standard deviation using the formula that we just talked about in the previous page here, as long as no more than 10% of its population is in each sample. So that shows us again the conditions will be the normal condition is the large sample condition, and then the 10% condition still needs to be satisfied for both samples. So we'll go ahead and check those conditions here, or in a minute here, when we actually get to doing some inference. Let's look at an example here. It says a fast food restaurant uses an automated filling machine to pour its soft drinks. The machine has settings for small, medium, and large drink cups. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid L dispensed by the machine follows a normal distribution with mean 27 ounces and standard deviation 0.8. When medium is chosen, the amount of liquid dispensed follows a normal distribution of 17 ounces with a standard deviation of 0.5. To test this claim, the restaurant manager measures the amount of liquid in each of 20 cups filled from the large setting and 25 cups filled from the medium setting. Let x bar sub L minus x bar sub M be the difference in the sample mean amount of liquid under the two settings. So average large sample and average medium. What is the shape of the sampling distribution? Look here, it tells us that large has a normal distribution and medium also has a normal distribution. So if we know that both parent populations have a normal distribution, then we know also that the sampling distribution of x bar L minus x bar M is also normal, right? In this case, we don't have to do the large sample condition, which wouldn't be met anyway, because we're told that the parent populations are normal. So we don't have to check any condition there. We can just go ahead and say, yep, the sampling distribution for the difference of sample means would be normal. B asks, find the mean of the sampling distribution. This is really straightforward, right? If we are looking for the mean of the sample, the mean difference, so we're looking for the average of this is what we're looking for. Well, we know that the average of the difference in sample means would be exactly equal to the average amount in a large cup minus the average amount in a medium cup, which were given as 27 and 17. So we know the average of the sample of the difference of sample means would be 10 ounces. Okay. You're hearing me stumble over my words a little bit here. This is it can get really confusing here when we're talking about the average difference of average is, right? So be really careful with your phrasing here. What we're saying here is the true average of the difference of sample means is equal to the difference of the true averages from each population. Okay. C says find the standard deviation of the sampling distribution. Again, the sampling distribution of x bar L minus x bar M. Find the standard deviation. Well, we just learned that formula on the previous page. The standard deviation of x bar L minus x bar M is equal to the square root of the standard deviation of L squared. Otherwise, it's, well, let me say this way. Let me be extra clear here. It's the square root of the sum of the variances, right? So we want the standard deviation of L of a sample from L would be standard deviation of L divided by square root of n. That's the standard deviation of the samples from L. And then we'd square that to get the variance, and then the same concept for the mediums. Or once we square this, we end up with sigma L squared over N, sorry, I should say NL, for the sample from the large cups, and NM. So then we end up with the square root of sigma L squared over NL plus sigma M squared over NM, right? And this is the formula as it was given on the previous page, so you can plug straight into that. That's the formula that's given on our reference sheet. So now we'll plug in the actual values. That gives us 0.8. That was the standard deviation from the large cup squared over, there were 20 large cups, plus 0.5 was the standard deviation of the medium cups over 25 medium cups. And we type that in the calculator. I'll spare you the time. We'll get 0.205 ounces. So this is the standard deviation of the difference in sample means from large cups to medium cups. Okay. In the next video, we'll talk briefly about the sample statistic that we'll use for difference of sample means.